Good morning, friend. Myself, Professor Prashant Mahajan. So today we are going to see the topic IR spectroscopy. So what is IR spectroscopy? What are the changes going to occur in the molecule when IR radiation falls on the molecule? That we are going to see today. Which type of vibrations are going to occur? That is also the part of the today's lecture. So IR spectroscopy deals with the infrared region of the electromagnetic radiation. So it can be analyzed by three ways. First, by measuring reflection. Second, by measuring emission. And third, by absorption. IR spectroscopy, it is also called as vibrational spectroscopy. IR spectroscopy is mainly used in structure elucidation to determine the functional group. So in case of IR spectroscopy, we are going to get functional groups. In the previous lecture, we have seen UV visible spectroscopy. In that case, we are going to get the lambda max value. Based on that lambda max value, we are going to determine the structures. Next, principle. Molecules are made up of atoms linked by chemical bonds. The moment of atoms and the chemical bonds is like spring and ball, that is vibration. So the characteristic vibrations are called natural frequency of vibration. So the two basic conditions are there for the IR absorption. That first is the applied infrared frequency should be equal to the natural frequency of vibration. So this is the first requirement for the IR absorption. And second requirement is that the molecule which is subjected to the IR radiation should have dipole moment. That are the two conditions required for the IR absorption. So let us see the next. When energy in the form of infrared radiation is applied, then it causes the vibration between the atoms of the molecules. So in the case of UV region, that electrons present in the atoms or molecules are going to excite. But in this case, the energy is not that much sufficient. So in case of IR radiation, the molecules are going to vibrate. Then absorption of IR radiation takes place, a peak is observed. So based on the different functional groups, different peaks you are going to get. So that is given in the next line. Different functional groups absorb characteristic frequencies of IR radiation gives the characteristic peak value. So IR spectrum of a chemical structure is fingerprint of a molecule for its identification. Means what? Suppose we have acetic acid molecule. Then in that case you will get a peak for CH3, that is carbon hydrogen bond. Then second peak you will get for carbon carbonyl bond. Then third peak you are going to get for carbon double bond oxygen. Fourth peak you are going to get for carbon single bond oxygen of hydroxyl. And fifth peak you are going to get for the oxygen single bond hydrogen. That is called as functional groups. And for each functional group you are going to get different IR absorption peak. So next is organic compound absorb electromagnetic energy in the IR region. As earlier I have explained that UV visible region causes electronic excitation due to sufficient energy, but in this case IR radiation causes only vibration in the atoms present in the molecule. So you can see in ultraviolet visible region there is electronic excitation. In case of infrared region there is vibration. In the case of microwave region there is rotation. So there are two types of vibrations. One is stretching and second is bending. So fundamental modes of molecular vibration can be classified into two types. One is stretching and second is bending. So first, stretching vibration. So it involves movement of an atom within the same bond axis such that The bond length changes without any change in bond angle in regular interval. That means in the stretching vibration, there is only change in bond length. Bond angle will remain same. In case of symmetrical molecules like CO2, that CO2 does not absorb IR radiation because there is no change in the dipole moment. So in exam, there will be the question like that, why symmetrical molecules does not absorb IR radiation. So you should answer like that, if there is a dipole moment or change in dipole moment, then and then that molecule is going to absorb IR radiation. So which are those examples? Like CO2, nitrogen is there, that is N2, O2, F2 is also there. That is symmetrical diatomic molecules are not going to absorb IR radiation due to no change in dipole moment. The next is non-cyclic system like aliphatic or open chain systems shows n minus 1 stretching vibration because this vibration describes only one directional motion. The second thing which is important for IR absorption is dipole moment. So as I earlier said, if there is a dipole moment, then and then that molecule is going to show IR absorption. Next is why it is going to show the IR absorption. So the electric charges, positive and negative, on the atom of the molecule experiences forces in opposite directions. As a result, spacing between the charge atom, that is electric dipole of the molecule, also decrease. These charge atom when vibrated absorb IR radiation. Then if the rate of vibration is fast, then it exhibit intense absorption of radiation and vice versa. Next is vibrational transition of CO, NH, OH, etc. occur due to change in the dipole moments that absorb higher radiation. So I'm saying again and again, if there is a change in dipole moment, definitely there will be the higher absorption. Next is symmetrical diatomic molecules. O2 and N2 does not possess electric dipole and cannot absorb higher radiation due to no change in the dipole moment. One more thing, if the symmetry is destroyed, then that molecule is going to absorb higher radiation. Hence the example is given. In the case of ethylene, the molecule is symmetric, so it is not going to absorb higher radiation. But if that ethylene is converted into bromoethylene, that means substitution of one hydrogen by bromine group, that will destroy the symmetry of the ethylene molecule. Hence, it is going to show the IR absorption. Next, when the polar molecule is exposed to IR radiation, stretching vibrations along the internuclear axis of the polar bond are seen. Hence, electron distribution changes and a change in dipole moment is seen. So remember the thing. First, stretching vibration occurs along the bond axis. Second, CO2 does not absorb higher radiation due to no change in the dipole moment. Third, non-cyclic system shows n-1 stretching vibration. Fourth, higher absorption takes place only when there is a change in dipole moment. Fourth, due to presence of positive and negative charge, there is there is forces in opposite direction, so the distance between the atoms decrease. Next, when the atoms are vibrated, then higher absorption takes place. If the vibrations of the charge atom are fast, then the bands are perhaps higher absorption bands are intense. Next, CO, NH and OH shows dipole moment. That's why it is absorbing higher radiation. Next, symmetrical diatomic molecules like oxygen, nitrogen does not possess electric dipole. That means it doesn't show dipole moment. Hence, O2 and N2 are higher inactive. If symmetry of the molecule is destroyed by substitution, then it will show the IR absorption. And last, when the polar molecule is exposed to IR radiation, stretching vibration along the internuclear axis of the polar bond are seen in electron distribution changes and a change in dipole moment is seen. So that are the conditions for IR absorption. Next, types of vibration. First, stretching vibration and second is bending vibration. So stretching vibrations are up to a type, that is symmetrical and asymmetrical. Bending vibrations, that is in the plane, out of the plane. In the plane, two vibrations are there: scissoring vibration, rocking, and out of the plane, wagging and twisting. So first, stretching vibration. So vibration or oscillation along the line of bond, change in bond length and not in bond angle. So first, symmetric stretching, that is the atoms of a molecule either move away or towards the central atom but in the same direction. You can see in the figure, both the atoms are moving away from the central atom, or it is coming towards the central atom but in same direction. That type of vibration or stretching is called as symmetrical stretching. Second is asymmetric stretching, that is one atom is approaching towards the central atom and second atom is departing from the central atom. So you can see one is going away from the central atom and second is coming towards central atom. That is called as asymmetrical stretching vibration. You can see in this also, this is atoms approaching, both the atoms approaching to the central atom or going away from the central atom. So this is called as symmetrical stretching vibration because both are moving in the same direction, and in the second case one is going away from the central atom, other is coming towards the central atom. So it is in the opposite direction, so it is called as asymmetric stretching vibration. Then next is bending vibration. So there are two types in the bending vibration: in the plane and second is out of the plane. So first is in the plane. So first, rocking vibration in the plane, bending vibration. So it is the vibration in which the atom swing back and forth with respect to the central atom, means it is moving in the same direction. So you can see in the diagram, that is the scissoring vibration. So both the atoms attached to the central atom moving in the same direction, that is swing back and forth with respect to the central atom. In the case of scissoring, as you know, scissor, that is both the atoms moving towards each other, that is called as scissoring. So we can see the definition: in the plane, bending of the atoms occur wherein they move back and forth, that is they approach to each other with respect to the central atom. That is called as scissoring, bending, vibration. So you can see in the diagram, this is rocking, both are swing back and forth in the with respect to the central atom, and this is scissoring, that is both are moving to each other, that is called as scissoring vibration. Next is out of the plane, that is first is wagging and second is twisting. So wagging means what? Now this is out of the plane vibration, that means what? Both the atoms are moving out of the plane or both the atoms going below the plane. So this vibration is out of the plane vibration. In case of the wagging, two atoms move to the one side of the plane, they move up and down of the plane. That means what? They are coming out of the plane or both are going down below the plane. That is wagging. But both are coming at a time and both are going down at the same time. That is wagging. In case of twisting, as we twist, like we twist the pages or clothes, like in the opposite direction, that means one atom is coming above the plane and second atom is going below the plane. That is called as twisting vibration. So you can see in the figure, that is both are coming above the plane, both atoms going below the plane, that is called as wagging. And in the second case, one is coming above, second is going below, or one is going below and second is coming above. So that is called as wagging and twisting, bending vibrations. So this is all about type of molecular vibrations. So these two are symmetrical vibrations, sorry, stretching vibrations, and these are the four bending vibrations. Thank you.